Okay, so I'm going to give you an update on some of the recent developments that have happened in the space of RTX, what we've been up to, showcase some of the impact that it's had so far on the industry with lots of eye candy. Hope you guys enjoy this, and also paint a bit of a vision for where we think this is going to go in the future. And we'll start with this. So this is the Reflections demo called Reflections that we showcased exactly a year ago here at GDC together with Epic. And it was a kind of a milestone in real-time rendering, given the visual quality that we were able to achieve for the first time in real time. So the quality here, of course, comes from ray tracing, right? We see ray traced reflections, ray traced beautiful area light shadows, ray traced ambient occlusion. So it's very expensive to compute this, very computationally expensive. So at the time, a year ago, in order to run this, we had to use a DGX station, which is a large workstation computer that we sell to researchers and universities. It comes with 4 Volta GPUs, the biggest chip that we make, and it sells for $60,000. Now, exactly a year later, we can run this same demo on a laptop, a gaming RTX laptop, which is, of course, a fraction of the power envelope. It's a fraction of the cost. In fact, I think you can build a PC for about $1,000 today that can run this demo. So that's a 60x reduction in cost if you compare it that way. So when was the last time in our industry that something improved by 60x within the time frame of a single year? So this is just a little bit to reflect back, what's happened in just a single year, the amount of improvement that's happened, the perspective that we have on what really the state of the art of real-time rendering is today. So the visual quality of that demo came from ray tracing. The performance jump came from RTX. The RTX is the technology, a combination of hardware and software that really forms the basis of what next generation graphics is. And it does this by accelerating both ray tracing and AI. On the hardware side, what this means is GPUs with RTX acceleration include Turing SM architecture, which is a new improved SM architecture compared to Pascal. Lots of improvements made, some of them specifically in order to accelerate workloads like ray tracing, make those better. Things like concurrent integer and floating point operations, enhanced L1 caching, things like that. Then, of course, the RT cores themselves, built specifically to accelerate ray tracing, in particular BVH traversal and ray-triangle intersection. And then tensor cores for hardware-accelerated AI computations. So this is where the performance comes from. This price or the cost improvement basically comes from the fact that we introduced RTX, this combination of features, to consumer graphics cards. So we started this 7 months ago at Gamescom with the introduction of the 2070, 2080, and 2080 Ti cards. And just a little over 2 months ago, we introduced the RTX 2060 that you see here, which gives you all these features for about $350, which is really an interesting price point for a feature set like this. In addition, at Gamescom, at CES, about 40 RTX laptops were announced as well, and the types of laptops that you can use to run a demo like the Star Wars demo now. And one thing that should illustrate how important ray tracing and AI is to us and the RTX feature set is just the fact that we basically renamed our top-of-the-line consumer GeForce cards, right? For over a decade, we had them named GTX, and it went from GTX to RTX, and this is the level of seriousness that we have behind this. So one reason, or one way to look at why ray tracing is so important to us and why we really believe that there's no other way to go for graphics in the future is to look at what modern rasterization does and what the high-end techniques do. So here's an example from Battlefield 1, not with ray tracing, and it looks very beautiful, right? It's a good-looking game, and it uses all the top-notch, high-end, typical rasterization techniques, things like shadow maps, screen space ambient occlusion, screen space reflections, all these things. And if you think about it for a bit, all of these techniques are basically trying to solve the same problem, which is that you can't, in rasterization, when you shade a pixel or a fragment, you can't look around you in the scene and try to figure out what's around you, try to learn about the lighting that's coming in, the visibility, and all these things. All of those techniques that are used in modern rasterization build some kind of data structure, whether it's a G buffer or a Z buffer or a shadow map or an environment probe or a voxel grid. All these things are data structures that contain approximations of your scene so that your pixel shader can look up into that data structure and infer what's around you. And so these data structures are, of course, limited, right? They have limited resolution, they have limited information in them, and in some cases it's extremely coarse, right? Like a depth buffer used for shadow maps, for example, is inherently limited in resolution. It doesn't scale very well in the distance. You get aliasing, all these things. And this is where ray tracing really addresses the problem at the root for all of these techniques. It gives you the fundamental tool to do exactly this sampling around the environment of your shading point. And this is the reason why with ray tracing you can get renders that are actually much closer to correct or completely correct. And it's why film rendering, for example, has been using ray tracing for well over a decade and haven't looked back, right? Now, this is not to say that any of these raster techniques are completely to be thrown away immediately and from one day to the other. We can just replace all this with ray tracing. It won't be quite that easy. We'll still need interesting tricks in order to make ray tracing work in games. But the key is going to be to add ray tracing and use ray tracing selectively in places where it really makes sense, and then over time we'll be able to replace or enhance a lot of these techniques by adding ray tracing where it makes the most difference. And because we think ray tracing is so important, we want to bring it to as many people as possible. And so this week at GDC, we're announcing that we're bringing ray tracing much further down the line of our product lineup, all the way down to GTX 1060 6GB Pascal cards. So on these cards, we're enabling a software fallback in the driver that replaces or that emulates what RT cores do on Turing RTX cards. And so by doing this, we can bring the functionality of ray tracing to tens of millions of gamers today without upgrading their GPUs, without having to upgrade. There's nothing the developer needs to do. The driver just exposes it and it just works. Of course, it's going to run quite a bit slower because the fixed function dedicated hardware is there for a reason, right? Ray tracing is still expensive. But it does depend a lot on the workload, what exactly the game does, how it uses ray tracing. The speed ups or the slowdowns that we're seeing in cases where we run it in software mode, vary from several times slower, where it becomes basically unplayable on the lower end cards, all the way to if the game just does a little bit of ray tracing, it's actually on the lower quality settings, for example, can be quite playable. So we're hoping that by doing this, we're getting ray tracing into the hands of many more players, and as well as developers, right? It's going to speed up the ecosystem and speed up adoption just by getting it into as many people's hands as possible. Now, the way that developers use ray tracing or access RTX underneath is mainly through these two APIs, DirectX through DXR, Microsoft DirectX ray tracing in DX12, and Vulkan. So for DX12, we worked very hard with Microsoft, very closely together to develop DXR, starting a couple of years back. And the first version of it was introduced again a year ago. The API is fairly low level, just like you're used to from DX12. It exposes things like BVH construction explicitly, memory management, synchronization, what exactly, how work gets submitted to the GPU as a typical DX12 mechanisms. And we're really quite pleased to see the fast adoption that we're seeing with developers. It's actually, I think we hit quite a nice balance with the API, and it seems to be quite successful. With Vulkan, we developed extensions that expose the same kind of mechanism. So it's actually the abstraction and the mechanics are very similar to what we did in DXR. So this is currently an NVIDIA extension to Vulkan. And we're working with all the other members of Khronos to turn this into a platform-independent and vendor-independent standard. So our extension there is used as an input for these discussions. So both of these APIs that I just talked about underneath talk to the same core RTX ray tracing driver. And I want to give you a little glimpse into the types of areas that we've been focusing on over the last couple of months. And of course, it's all about performance, right? We've added over 25 compiler optimizations since we launched RTX, since we launched Turing. These are just ray tracing specific compiler optimizations. There's lots of other compiler work going on at NVIDIA that goes into the generic shader compiler. There's many stages of compilation going on in the driver. Of course, with an API like DXR, compilation of shaders is an extremely important piece. We often see applications with many hundreds of shaders, very complex shaders. So it's critical that we compile these efficiently. The compile times have to be short. They have to compile to efficient code, and they have to be scheduled efficiently to all run together efficiently. So lots of work going on there. We're also by no means finished. It's all, a lot of it is in flight. We've reduced the command memory footprint, in some cases quite dramatically. So this is especially if you have many command lists recording commands at the same time, which happens quite often in multi-threaded applications and ray tracing specifically. Memory is a scarce resource, and so we've worked quite hard on improving this. And then we've improved asynchronous compute overlap. So this is an interesting one because on Turing, we actually have a way to run asynchronous compute work interleaved with or concurrently with graphics work on a much more fine-grained level than we could on Pascal. So on Turing, we can actually run graphics and compute work on the same SM. So we've done a lot of software work in order to make sure that applications hit this path as much as possible so that we can overlap the ray tracing work, which is mostly compute type things, with other work like graphics. And that's especially important for BVH builds because they tend to be kind of bursty in how they use the GPU, just the utilization. And so if you can hide this behind other work like G-buffer fills or shadow maps or skinning or something like that, then that can be very beneficial. Speaking of BVH builds, just the construction of BVHs is a pretty important topic as well. For all the scene that happened, or the scene that's being ray traced against in a given workload, we have to build BVHs for all the objects. And many of them are dynamic, which means that BVH builds or refits happen many times per frame. So it's very important that this is super high performance because it directly goes into your frame time, right? So the throughput of the build itself, we've been able, just over the last 3 months, that's what these two driver versions compare, that's about a 3-month time span. We've been able to improve this by 36% on average and up to 72% in some cases. The update throughput, so update is exactly this BVH refit, which happens in some cases, many hundred times per frame, has gone down by 16% on average, up to 38%. And then CPU performance, equally important, right? If we do something many hundred times per frame, it's too easy to get CPU limited, which of course we want to avoid. So we've put some effort into improving that as well. So 21% on average improvement there, up to 43. And then we did all that while also reducing the memory cost for BVHs by 10% on average. So a lot of work going into that as well. Same thing here. It's getting better every day. The team's working super hard on making this better in the future still. So a lot of the performance work is happening on the software side, and it's not just the RT cores in the hardware. All right. So now we have we've built a very efficient ray tracing machine. We've got a super fast hardware, ray triangle intersection hardware, BVH intersection hardware. We've got an efficient software stack. But despite all this, we're still hitting realities when we try to ray trace full scenes in real time, right? We don't quite have the ray budget to just brute force ray trace or path trace everything till convergence. And so what we end up with typically in real situations is a situation where we have only a few rays per pixel, like a handful or 3, 4, 5. And so for any kind of distribution effect like we have here with ambient occlusion, we end up with a lot of noise, right? And the only way to really get rid of this is either brute force it, have many hundreds of rays per pixel, or run a denoiser. So denoising is a very important topic, and we have we've seen a lot of research going into it over the last 2-3 years or so. And let's look at some of those results. So here's one sample per pixel shadow, ray traced shadow. This is sky shadow. It's some kind of an overcast sky, which is why the shadows are pretty soft. There's shadows from the trees there, which are kind of semi-transparent. And if we run a denoiser over that, it looks like this. Not too bad. Now let's compare it to the ground truth, which is many hundreds of samples per pixel. Okay, flipping back and forth. It looks like on the projector you can almost not see a difference at all. There's a slight difference, but we got pretty close. Now compared to shadow maps, looks like this. So this is the classic raster solution, very different, right? You see all the typical artifacts. They don't handle, of course, this semi-transparent leaf situation very well. They're pretty much equally sharp or blurry everywhere. You've got people that look like they're floating. There's Peter panning going on. All the typical raster problems. Now reflections. It's kind of a similar picture. So here's a 1 sample per pixel reflection input with different roughnesses. And after denoising, it looks like this. Compared to ground truth, again, a small difference, but not too bad. And SSR, so the typical raster solution with quite a large difference. Okay, so denoising is clearly super important in order to get ray tracing to work in real-time scenarios. But they're not easy to write, right? It's not easy to get to this level of quality that I just showed you for denoising, and it's even harder to make those denoisers fast enough so that they're okay to run in a typical, like every frame in a game, and in some cases, multiple times if you're doing multiple lights or multiple effects. And so I'm happy to announce that we're sharing the denoisers, our best denoisers that we have in an RTX denoiser SDK. There will be initially denoisers for shadows, reflections, and ambient occlusion. It's going to be a lightweight C++ and HLSL library without any graphics API dependencies, so it'll be possible to plug this into both Vulkan and DX12. And we're shipping this or making it available as source in a couple of weeks from now in May. So we're hoping, or we're building on the denoisers that we've built so far in order to make this problem just go away for developers, right? Ideally, a denoiser isn't something that developers have to worry about. They should just grab something that's already available. There shouldn't be a reason to reinvent solutions to this problem because everyone working on ray tracing is going to have to do some kind of denoising. And so I think that making this available is going to give ray tracing quite a nice boost in adoption. Okay, now we've looked at denoising and ray tracing. Let's see if we put them all together, what can things look like in an actual practical application and look at some actual games. And we'll start with Battlefield 5. So Battlefield, in case you don't know it, it's a competitive multiplayer FPS, up to 64 players. It's developed by DICE in Sweden on top of the Frostbite engine, which has a long history of pushing graphics to the limit, right? And they did it again here by incorporating ray tracing as actually the first shipping title to use DXR and RTX ray tracing. Battlefield uses ray tracing for reflections, both specular and slightly glossy reflections. And I do want to mention that DICE really deserves a lot of credit for making this work and for doing the early adopter work, essentially. When they started the work there, we were still in the middle of driver development. They didn't have a lot of access to the hardware in the very beginning because it was all coming in pretty late on tight deadlines. And so the fact that they were able to ship this in November is really impressive and deserves a lot of kudos. I also highly encourage you to go see their talk, which I think is later today, where they go into a lot of the technical details that were required to make it happen. Now, as I mentioned, we put a lot of effort into driver optimizations and making the driver faster. At the same time, game developers, and in this case, DICE has put a lot of work into optimizing the way they use the API, the way they use ray tracing. And so over the course of the last couple months, we've seen very nice speed ups coming in. So this is frame time or FPS numbers with everything cranked to ultra, right? Which on a 2080 Ti, it's what customers expect. They want to crank everything up. So we started out with 44 FPS in November, which frankly is not quite where we wanted to be with this, because on a game like Battlefield, if you're under 60 FPS, you basically don't have to show up. It's not, you can't be competitive. Today, or the latest data point I have is 75 FPS. That was a month ago. And this is without DLSS even, so we'll talk about DLSS a little later. So this is just to point out that we're still working on this, on performance, still getting better all the time. So you can expect more improvements there. So without further ado, I want to show a little trailer to just showcase what this looks like today. So this is all in-game graphics. Okay. Thank you. All right, beautiful stuff. So this, by the way, also an in-game screenshot. I just went somewhere in spectator mode and hit print screen, and this comes out. So, all right, let's look at another game. This is Metro. released about a month ago with both ray tracing and DLSS at launch. It's the latest installment and the biggest by far so far of the successful Metro series developed by 4A Games. And it takes you on a journey through post-apocalyptic Russia. It's an extremely moody game, kind of a little creepy, and it's very nice what they've done with just the art direction combined with ray tracing. And this, by the way, is an in-game shot, right? So it looks like this in the game. So in Metro, ray tracing is used for dynamic global illumination. The game computes one bounce of indirect light from sunlight. So looking at the RTX off picture here in the top left, you can see it starts from direct light hitting the floor and then some kind of ambient term, kind of what you would do usually, ambient plus some GI approximation that you typically do with raster light probes and things like that. Ray tracing is used here to compute with a single ray per pixel, or in some cases, depending on the quality setting, a ray every 2 pixels. Compute an AO pass and a GI pass with the same ray. And then multiply those two terms or add them to the lighting terms that the engine is already computing for the raster passes. So it's kind of an artistic mix, which is very much on purpose because the art direction for this game had to go a certain way. A lot of the, similar to Battlefield, a lot of the assets and the art and the style was already done and locked down before the developer actually had the chance to look at ray tracing, which makes this very challenging, right? You can't just throw away the gameplay because you have new lighting effects, especially in a game like Metro, where a lot of it is about stealth and dark corners and things like that. So they had to make sure that this still looks right with both RTX on and off and doesn't break gameplay. So with ray tracing on in the bottom right, we see how light nicely bounces off the floor and onto the ceiling. So we get this one bounce indirect illumination. And actually, if you look at the missing board there in the ceiling, without ray tracing, there's kind of a lot of light in there, and it's darker, above the ceiling with ray tracing on because the bounce light just doesn't go there, and it's something that the raster solution can't approximate. So let's look at a couple of examples. So this is what it looks like by default. No ray tracing. Doesn't look bad, right? Quite a pretty game. If we turn it on, suddenly it looks a lot more natural. Things just seem to fit in better. I'm going to flip back again. If you look at the snow plow there and the railing on the train car, suddenly it seems like it's glowing and it doesn't really fit, right? And there's probably some sort of not enough resolution in the voxel grid, or I don't know what's going on, but it's essentially a light leak. It just doesn't happen with ray tracing if we get the correct solution there. Here's another example. No ray tracing and ray tracing on. So you can see how the extra occlusion there really adds a lot of depth to the image. It's almost like someone turned on the 3D, right? Here's another interesting one. So I'm going to flip back and forth on this one a couple times. So look at some of the details, like this ball, for example, the shadowed region of the ball. If I turn RTX on, it receives the bounce light from the floor, right? So the shadowed region gets a little bit brighter. If you look at the pillow that's sitting on the floor, I'm pointing at my screen. If you're looking at the pillow that's sitting on the floor on the very right, it looks kind of like it's floating. And with ray tracing, it gets a nice contact shadow. It really looks like it's sitting on the floor where it belongs. And then very interesting, on the very left side, this board there, or the wall, kind of looks pretty bland without ray tracing. If I turn it on, it gets a nice indirect shadow. So indirect shadow from a dynamic object is not something you typically see in a game. And then let's look at yet another one. So if you look at the shoe on the couch, it's kind of the back of it looks like it's glowing a little bit. That seems to be another type of light leak or something. And again, it looks just like it actually belongs there if we turn on GI. So this is Metro. Again, a very pretty game. Uses ray tracing for very nice GI effect. I highly recommend you check it out. All right, let's take another one. This is Control. an upcoming game by Remedy. Remedy is a Finnish developer, best known for Quantum Break and Alan Wake and Max Payne. They also have a history of pushing graphics to the limit, so it hasn't been a surprise to us that they were one of the first developers to jump on ray tracing. And Control is notable because it's going to be one of the first games to incorporate not just one effect with ray tracing, but actually 3 at the same time. So they're going to do ray traced shadows, ray traced reflections, and ray traced GI all at the same time. So let's just take a look at what this looks like. If I can, yeah. The Research Bureau. There's some supernatural forces going on, so you see people floating in midair. It's not a bug. So look at the reflections on the floor. It's almost like you can feel the wax that they use to clean it. RTX off. Still some SSR reflections. Doesn't look too bad, but much less fidelity, of course. Look at some gameplay.
Are you ready? Let's go.
And you'll see in a moment, a lot of the environment is actually dynamic. A lot of it is destructible, moving objects. There we go. You can make a real mess of this place, and the lighting is fully dynamic. There's a little bit of baking going on, but most of it is completely dynamic. No matter how much you make a mess of it, the lighting always looks right every time.
Choosing a director tied to all objects of power in terms of
turning GI on and off. You can see how it doesn't look quite right. Again, some things seem to be glowing.
The white, non-space, the ever-present
specular reflections.
Of
course, works on dynamic objects.
All linked, intrinsically tied in terms of who controls them.
And pixel-perfect contact shadows or shadows on even difficult objects. Like, look at the binder that's on the desk. You get a very thin object that still has a shadow. Very hard to do with faster. And of course, completely dynamic.
On the classified, but we can talk in broad.
All right, so this is Control. Super pretty game. I can't wait for this to come out. It's going to be out late summer. And yeah, it looks like this. This is, again, an in-game shot. I think for most of us, if you had seen this shot, not too long ago, at least I would have thought it comes out of an offline render right now. Here we are walking through this environment in real-time frame rates, and not only walking through it, but interacting with it and destroying things, blowing stuff up, and it always looks correct. So very impressive stuff. All right. So last but not least, this is a fun one. You might have seen this one in Jensen's keynote. Quake 2 RTX. So a while ago, a couple months ago, Christoph Schied, who's an ex-intern at NVIDIA, added path tracing to Quake 2. Quake 2, of course, heavily modded and modified for decades, right, since it was open sourced in, I think, 2001. He added path tracing and filtering, denoising to it, and it made quite a splash, and we liked this so much that we doubled down on it and worked with him to add even more effects. So we added a whole bunch of new features like HDR sunlight, completely dynamic time of day, volumetric lighting, fluid simulation, GPU particle fluid simulation for explosions and smoke. Of course, reflections and refractions on the water. It's fully path traced. Not a single triangle in this demo is rasterized. It's all ray traced, primary to primary rays plus all the effects. Because it's path traced, you basically get all the effects within the single unified algorithm that path tracing is. So you get soft shadows, reflections, glossy, indirect diffuse, everything. We added some new materials to showcase the physically based nature of the rendering. And we even added SOI support, if you can believe it. And this is going to be contributed back to the open source community, so we're going to make this available. There's also a talk on this together with Christoph and our lead programmer on this project, which I think is tomorrow at 2, so be sure to check that out. I could watch it much longer, but that's good. Okay, major engines. Unreal and Unity are the most important and the most popular game engines in the world. They represent together about 90% of the world's games. So this week, both of them announced that they're adding ray tracing and DXR features to their engines. And this is going to be a huge deal for developers using those engines, because essentially ray tracing, instead of having to really deal with the low levelness that is the DX12 and DXR API or the Vulkan API, it becomes a turnkey solution. It's essentially a checkbox. It's a tiny little bit more complicated than that, but not that much. So this is really amazing for just the adoption that we're going to see with developers. And I can't wait to see the first indie game comes out that enabled RTX just by clicking a button. So in the case of Unity, this is an example for what it can do in Unity. The image you're seeing here is from a collaboration between Unity and NVIDIA. It was rendered in real time in the engine with RTX ray tracing. And it's from a shot or a short movie that seamlessly blends together shots from a real car with a car that's rendered in real time, and you can't tell the difference. It's really impressive. I encourage you to check it out on their website. So this is this is targeted at virtual production, but of course it's still all in the same game engine, so it's going to be available for whether you do production or games. The feature is going to be there. Unity is going to be making this available as an experimental version for anyone to try on April 4th on GitHub. Now on the Unreal side, you can actually already try this. Ray tracing is integrated in a preview build of Unreal Engine 4.2.2 that's already available for download. And it has a whole bunch of nice features that are ray tracing enabled. So we get ray traced reflections, ray traced ambient occlusion and GI, and also ray traced area lights, which is a super nice feature. So this is rectangular area lights. To use them, literally all you do is drag a new light type into your scene, and you get beautiful area shadows with nice contact hardening that are basically impossible to do with rasterization. So this is really as easy to integrate as it gets. What you're seeing here is another feature they added, which is a reference path tracer. So it's handy for computing reference solutions of your scene to see where maybe your real-time rasterization path doesn't hold up quality-wise. So it just runs in the engine like that, and you can see this little art installation I put together there. To see what it can really do in real time, I have the pleasure of showing you a short movie that Epic just unveiled probably 2 hours ago or so in their keynote. And this is all running in real time on a single RTX 2080 Ti, if it loads. All right. So super impressive stuff, I think. What they did there with the character rendering, of course, characters, human characters especially, is super hard to render. Things like skin is really, really difficult. And clearly having ray tracing in the engine is going to be extremely powerful for developers to enable things like this. Now, empowering developers requires great engines, great integrations, but it also requires good tools. And we've been doing a lot of work to enhance our tools to better support ray tracing over the last year or so. So I'm happy to announce today that we're releasing Nsight Graphics 2019.2. This is available today. And it comes loaded with DXR support, new features and improved features. So it's got a shader table viewer. If you're familiar with that API concept, it's basically a batch of memory that tells the system where to find shader resources and how they're connected to objects in the scene. It can be a little tricky to get that right if you're programming against the API, so having a viewer for that is really, really handy. Visualizes all the resources that are referenced there. It's got a BVH viewer that helps you visualize. You're seeing the different objects instances, which can sometimes be a little easy to lose track of, and visualize the flags that they're built with, which is also very important to get right for right performance. C++ frame capture, super handy tool, allows you to take a single frame of your game, just capture it, and save it out as a Visual Studio project that compiles into a little program that will just re-render that same frame all the time. And it's really handy to have this isolated, self-contained little program for debugging and profiling. Then we have Nsight Aftermath, which is DX12 crash debugging, also with DXR support. If you've ever written a DXR program, it can be quite frustrating. If you crash, you basically get no information whatsoever about why. So Aftermath tackles this. It inserts markers into your command stream in order to figure out which one of your commands caused the crash. And then if it was something like a dispatch raise call for ray tracing, it will actually point you to the source line in the shader that's responsible for the crash. So super handy and a huge time saver. Range Profiler shows you where your time is going within a single frame, shows you things like overlap of different workloads on different command queues, and of course also with support for all the DXR commands. And GPU Trace shows you the GPU utilization, so the visualization of a command over time and how well utilized the GPU is, what your occupancy is. So this is 2019.2 available now. 2019.3, I want to mention this one because we have some really cool DXR features coming up there. This launches in May. We'll have the metrics graph, which is a sub-feature of GPU Trace, which allows you even more detailed insight into what your command is doing and what it's limited by. So you'll be able to see performance monitor that the hardware captures. Things like can't issue reasons. Why is your instruction stream stalled, right? Things like cache hit rates, and also things like utilization of the RT cores during ray tracing. And then we have the shader profiler. This is also an exciting one because up until now, if you execute a dispatch raise command, so the main ray tracing command in DX12, it can kind of be a bit of a black box as to what it's doing and where it's spending its time, because potentially there's hundreds of shaders being executed more or less at the same time. And you kind of have no insight into what the bottleneck is. So Shader Profiler will show you exactly this. It'll show you a list of shaders, and you can sort by where the time is spent. It's a PC sampling-based implementation, so it's going to be very accurate and tell you exactly where the time is going. I should also mention that our friends at Microsoft have released about a week ago a new version of PIX. So it's their DX12 profiling tool that also has a lot of these DX12 features. So they have a BVH viewer and a shader table viewer as well. And we also have Nsight Systems, which is kind of a complementary tool to Nsight Graphics, where in Nsight Graphics you look at a single frame at a time. In Systems you look at many frames and a timeline with potentially millions of events. It's a very lightweight and efficient way of looking at this. And for example, figuring out why your application is stuttering. Like, what is that one frame doing that's taking twice as long as all the other frames? So very handy there. Another important resource for developers is our new best practices guide. This just went live just before this talk. And we've been collecting learnings that we've had since basically we actually started shipping games, working on shipping titles. There's always something that, when the rubber meets the road, basically, and we start turning the API usage from samples into actual shipping games, there's always things you can learn. And now, in order for everyone to benefit from these learnings, we've put together this best practices guide. So it includes lots of learnings from our dev techs that are working closely with the developers, and also the driver teams, or our team, pointing out what you have to do in order to hit the right fast pass in the driver and get best performance. We'll be, of course, updating this as we learn more about what works well, what doesn't work so well, best practices in general for the API usage, but also implementation-specific things. So also as the driver software stack progresses, we'll be adding lots of information. There is a talk tomorrow by Alex and Pavel called DevTech's Guide to Ray Tracing, where they go into a bit more, or much more detail on some of these techniques, and I encourage you to go check that out. And then finally on ray tracing, we have a ray tracing gems book, similar to the gems books that you might be familiar with already. Eric Haynes and Thomas Akanin-Miller have again done a fantastic job of pulling together industry experts from all over the place to submit and to share their expertise and their learnings on ray tracing. Lots of authors, 64 authors. It's an amazing book. I recommend, if you're working on ray tracing, you should be reading this. Best of all, it's actually completely free. You can go to this website and just download the entire PDF for free and share it with anyone. It is also a physical book that you can buy. In fact, I think it's here at the bookstore. So you might want to do that as well. Especially if you want to get it signed, there's a book signing from as many authors as we can find here at GDC. Many of them are here and are happy to sign the physical copies today at 4. And at 5 o'clock, Eric will be attempting to describe every single chapter in the book within an hour. So I'm curious to see how that goes. All right, let's switch gears and talk about AI, kind of the second pillar of RTX. And if you also grew up trying to render realistic pixels the hard way, then AI can kind of seem like magic, right? So what we're seeing here is a GAN, a generative adversarial network, that has been trained on landscape pictures together with semantic segmentation maps. And thanks to the tensor core's acceleration, we can, in real time, paint these segmentation maps and have the network infer photorealistic pixels from that. And so you can see how easy it is to generate some realistic landscapes there, change the style completely just by changing the semantic from grass to snow. It turns into a winter landscape. Notice how the tree lost its leaves because the network knows that trees typically don't have leaves in winter. So super impressive stuff, and the reason I'm pointing it out is really there's an enormous power behind AI in the capability to generate pixels that weren't there before. Like it can essentially make stuff up, and it's pretty good at it, right? If it's trained, it's been trained with the right things. Notice how it even renders the reflection of the tree in the water puddle. So extremely powerful stuff. Now, the question is, how do we turn this into something that's useful in the context of gaming, into an actual product? And the idea, or the product that we came up with, is called Deep Learning Supersampling, or DLSS. And the idea here is to have the game render a lower resolution than the target frame that's aliased, so one sampler per pixel, which saves a lot of rendering time, right? Lower resolution, no anti-aliasing. Send that through a network, and then hopefully we can make the network fill in the remaining pixels and upscale it with very high quality. So of course, the goal has to be, or the bar here has to be native resolution, 4K or whatever we're upscaling to, with TAA, which is essentially the industry standard for games today. So this also sounds a little bit like magic, but it turns out it actually works pretty well. So how are we doing it? First of all, we have to train the network. So in order to get high quality network weights or high quality training, we do this per title. So in this example, we've got Battlefield. So we run the training for Battlefield, look at many different locations in the game, all the different levels, as much different content as we can. And we train it on our supercomputer called Saturn V. Once the weights are trained, once the network is trained, we can deliver the resulting weights through the NVIDIA driver just via an update. The input into the training are 3 buffers, essentially. So 1 sample per pixel, low resolution or low sample count buffer, very aliased input. The motion vectors that the engine typically computes out anyway for other effects. And then a reference image that's the exact same as the 1 sample per pixel one, except it's got 64 samples per pixel. So high quality anti-aliased image. And we train the network on sequences. That's why you see this little animation here, in order to train it for temporal stability as well. Now, that sounds pretty straightforward on a high level. Turns out once you try to actually make this work, there's lots and lots of challenges, including which locations do you train? How do you make it so you don't train too much and not too little? How do you get even the motion vectors out of the game engine because they're very often broken? Or if you see a reflection, the motion vectors are simply not correct because they can't be. It's very difficult to debug. It's very difficult to operationalize in the sense that we want to, of course, keep the round trip, the delay between getting a new build from the developer of the game to having new weights shipped as short as possible. So lots and lots of work is going into and has gone into making this work well. There is a whole talk on it, not just the training part, but on DLSS in general, which I think is also tomorrow. Now, once we've got the training set up, the game integration is relatively straightforward. So we've got these 2 parts in the pipeline. Blue is what the game engine does. Green is the NGX API. NGX is a component in our driver that's responsible for talking to the neural network infrastructure. And so we let the game render a frame at lower resolution. NGX tells the game what the resolution should be in order to get the most bang for buck out of DLSS. It feeds it into NGX, which, so the input on that pass is going to be the 1 sample per pixel, quickly rendered image plus the motion vectors. And it gets back a feature enhanced image. So that's the first phase of the network. The game then does its typical post-processing, because first phase happens without post-processing on top, and hands it to a second neural network that does the final res upscaling. So the interesting thing here is that, of course, both of these phases are neural networks, which means they have constant cost, right? They're resolution dependent, but they're not dependent on what's visible in the scene. So the more expensive your frame is to render, the more bang for buck you get out of this system, because the upscale cost or the DLSS cost is constant. Now let's look at what kind of quality we're getting, and if we can really rival, in this case, 4K native with TAA. And so I've put these 2 images next to each other. One of them is TAA at native resolution. One of them is DLSS upscaled. And it's really quite hard to see the difference. And to be honest, I forgot which one is which. But it doesn't really matter, and that's kind of the point. So in this case, it works extremely well. The reality is, to be quite frank, we win some, we lose some, right? In some cases, TAA works better. In some cases, DLSS actually looks better than native res TAA. TAA, of course, has its problems. Often it's a little blurry. You can get ghosting because of the temporal aspect to it. It doesn't handle alpha transparency so well. In the DLSS case, when it fails, it can flicker sometimes, which is often due to just not enough training, not enough temporal training, or it could over sharpen, which can cause artifacts. So it's a bit trading blows, right? One thing to note is that TAA has been used for years and optimized and tweaked for a long time. So it's relatively safe to assume that it's not going to get much better than it is today. DLSS is very different, right? Still very new. We're training, retraining, improving the networks all the time. We're improving our methodology all the time. There's lots of room for improvement and lots of headroom for us to keep researching this. So the other thing to note is, of course, we're comparing these 2 different qualities, but one of them came from a much lower resolution and alias picture. And the whole point of it was to exploit that for performance boost. And so this is what we get as a result. Here's Metro. And by turning on DLSS, we get up to 30% speed up, just like that. So as a result, we can actually run Metro with ray tracing on at 60 FPS on all the RTX GPUs, all the way down to 2060. This is even with high ray tracing set to high at 1080p. Battlefield, similar, we even get a 40% speed up. And in this case, we can run it at 60 FPS on a 2060, even in 1440p. With medium RT, which really looks very similar or not that much worse than high or ultra because of the way the game allocates the ray budget. So it focuses on the areas of the frame that have reflections that are most visible. So you're not sacrificing much and you still get 60 FPS. So very cool to see this come together and actually work out. And it's getting better every day. Now, a little bit of a vision of where we think AI and graphics is going to go. This are just some of the topics that our research teams are looking at. We do think that AI, it doesn't stop at DLSS, right? There's lots and lots of things that you can imagine where AI can be used in graphics. Some of them are a little bit related to DLSS in the sense that they're kind of like a post-process-y kind of thing, super resolution, motion blur, defocus blur, things like that. But there's no reason to not think about ways to incorporate AI into, much deeper into the rendering pipeline. So one vision is to build smarter renderers where at every step along the rendering pipeline, there's something happening with AI. AI is helping the rendering itself. So, in a way, you can look at this from an angle where traditional rendering kind of changes into something that instead of generating an image, generates the input into some AI pass, right? And then AI is the thing that actually generates the final image. So at the bottom, you see some research that Jon Hasselgren and Jakob Munkberg have been working on. So this is defocus blur with a single sample per pixel input and using AI to generate a nice, proper depth of field. All right, so in summary, I think we're in a really exciting time for real-time computer graphics. Looking back just 1 year, the absolute top end in terms of quality that you could get was by turning up the knob to the max in terms of what you do with rasterization techniques, right? Polish them as much as possible, use as many of them as possible. Just 1 year later, the landscape has changed quite a bit. If you want top of the line, the highest quality real-time graphics, it does mean today already incorporating ray tracing and AI in this case for performance boosts. So of course we're expecting to see a lot more of that, right? We expect ray tracing to take a bigger and bigger place in the rendering pipeline, and the same thing goes for AI as well. Now, today we've seen a lot of things in this talk. So we've talked about more content that's coming. We're of course working with essentially every game publisher there is on RTX features. We're seeing upcoming games like Control, fun projects like Quake 2. We're seeing ray tracing come major engines with Unity and Unreal. We have a much larger install base starting, by the way, this will come out sometime in April with the driver update with ray tracing running on GTX cards. We have the Denoiser SDK shipping in a few weeks as source to help adoption and help people develop ray tracing applications. Much improved tools improving all the time as well as performance, software stack, a lot of work going into optimizations there. We're seeing deeper integrations of ray tracing into games. Again, Control, a great example that uses ray tracing for three effects rather than just one. And we'll also start seeing games that are from the ground up authored with ray tracing in mind, right? Where the assets are created and actually tested and lit with ray tracing rather than ray tracing kind of being tacked on after the content's already fixed. So that's going to make a big difference as well. And then, of course, AI is getting smarter all the time. We keep training it, improving the methodology, keep researching it. So things like DLSS and other techniques for having AI in rendering are constantly improving as well. Okay, as a final little showcase, I've got something that the team has worked on internally for a while. If you've been following our RTX announcements, then you might be familiar with the Sol demos. So we have a third installment of this, and I hope you enjoy. Again, of course, rendered in real time. All right, thank you.